guys, I'm Jill Brady, the science lady, and we're going to learn about magnetic fields. So, hey, wait, where are the lines? Do you see the lines? Do you see the lines? They're imaginary. That's because magnetic field lines are vectors that show the direction and strength of a magnetic field. They go through, but you can't actually see them because they're not real. They're just to represent the strength and direction of the poles. So, the number of lines that go through an area is called the magnetic flux, and that indicates the strength of the field. The more the lines, the stronger the field. So, because north is attracted to south and vice versa, the lines end up actually forming closed loops because it goes north, south, and it's attracted to each other. These are magnets. Magnets always have a north pole and a south pole. North is attracted to south and vice versa. Ready? They love each other. But the other side, now we've got north on north, and they don't stick together. See? Oh, no. You see this? This is a magnet. This is polarized. It has a north pole and a south pole. If I were to cut it in half, zip! See, this is thinner. It still has a north pole and a south pole because the magnetic they polarize themselves. So north is attracted to south. Whoa! See, it just picked that up. And see, so this is north and south. They're attracted to each other. But if you flip it around, now we've got north and north. Oh no, that's repelling. And fun fact, the Earth is one big magnetic field. It has a north pole and a south pole. So if you have a smaller magnet, the south part will spin around and point to the north. That's how compasses work. So what happens when magnetic fields interact? Interaction. So, interaction between magnetic fields, they both provide forces and then they provide a force on each other. So the north pole field from one magnet will attract the south pole field from the other magnet along in the opposite direction of the magnetic field lines. But the north pole field from one magnet will repel the north pole field from the other magnet in the same direction as the magnetic field lines. See this picture. For more, consider the following. But that's not all. Let's find out about magnetic fields due to electric current with our friend Veronica, the Wiener Kid.
Thanks, Jill. I'm going to go over the 3 right-hand rules with you guys. The first method is to determine the direction of a magnetic field relative to the current of the direction of the conventional current.
Continue.
Okay. So imagine holding a wire parallel to your body with your right hand. Your thumb represents the direction of the conventional current, and your fingers represent the direction of the magnetic field. The second method you can use is to determine the direction of a magnetic field produced by an electromagnet relative to the flow of the conventional current. So imagine holding an insulated coil perpendicular to your body. This is hard for you to represent. Okay, your thumb represents the flow of the conventional current. Positive goes into the south end of the coil, and negative comes out of the north end. So your fingers are the direction, once again, of the magnetic field. They go around. Alright? The third method you can use is to determine the direction of the force on a current-carrying wire in a magnetic field. If you have your hand out flat, your thumb represents the direction of the conventional current, your fingers are the direction of the magnetic field, and going onto your palm is the force on the wire. Now I'm going to go over some magnetic force formulas with you guys. F equals I times L times B times sine theta, where F is the magnitude of the force on the wire, I is the current of the wire, L is the length of the wire, B is the field strength measured in Teslas, and the sine theta will be the angle of the wire compared to the magnetic field. Good. The second magnetic force formula that you need to know is F equals QVB times sine theta. Or once again, F is going to be the force on the particle moving in the magnetic field, which is equal to the product of the field strength. the charge of the particle and the velocity. So force is the force of the magnetic field on the particle. Q is the charge of the particle, of the electron, I guess. V is the velocity, B is the field strength, and then again, sine theta is the angle of the particle compared to the charge.
What's this? How does it work? Well, it's an electromagnet. Let's go to Claire to find out more.
Hi, I'm Claire, and we're going to talk about how an electromagnet works. An electromagnet consists of a soft metal core made into a magnet by the passage of an electric current through a conductor surrounding it. Basically, they work by the application of electricity creating a magnetic field. Factors that affect the strength of an electromagnet are the nature of the core material, the strength of the current passing through the core, the number of times the wire is wrapped around the core, and the shape and size of the core. The direction of the flow of the current determines the north and south poles of an electromagnet. Where the current flows from is north, where it flows to is south. The soft metal core has the effect of multiplying the magnetic field. Electromotive force is the voltage given by the battery, not actually a force, and therefore is measured in volts. Here is my electromagnet. I have a power source, I have wire, I have a core, and I have a paper clip, which I'm going to try to pick up with this magnet. So what you want to do is turn on your power source, and here I can control the voltage. So I'm going to turn it up. That's turning up the electromotive force, and there I have the paper clip. Thanks for watching, guys, and remember to always ask a parent before trying science experiments at home.
Reporting live from Washington, D.C., this is Jill Brady, the Science Lady, going to Anna Rice for how a DC motor works.
Hi guys! Have you ever wondered how a direct current motor works? Or what a direct current motor is? It's a device that converts direct current, or electrical energy, into mechanical energy. It usually relies on the forces produced by a magnetic field. The DC motor has three main parts. The first one is the armature, or wire coil, which is made of many loops of wire mounted on a shaft or axle. The second part are the brushes, which are made of graphite and connect the commutator to the wire loop. And the third part is the commutator half-ring device, which rotates with the loop. A direct current motor is basically a modified galvanometer, which is a device that can detect and measure small electric currents. The galvanometer is made of a loop of current-carrying wire, which is placed in a magnetic field. According to the right-hand rule, which you learned earlier in the video, one side of the wire is forced up while the other side is forced down, causing the loop to rotate. The galvanometer can be modified to rotate more than 180 degrees by reversing the current through the wire loop. This is done by forming an electric connection between graphite brushes and a ring split into halves, called a split ring commutator. The commutator rotates with the loop and is set up so that each half ring changes brushes when the wire is exactly vertical. Changing the brushes reverses the current, allowing the loop to rotate past 180 degrees. This process, repeated over and over, creates an electric motor. Here you can see a simple diagram of a DC motor. You've got your magnetic field at the top with your wire loop going through it, which will rotate. Here, the half rings are the commutators, which are connected to the graphite brushes, shown here. As the loop rotates, the current changes here, causing the loop to rotate and spin in circles. So now, joining us to talk about how a generator works, Nicole.
Thanks, Anna. For all of you that don't know, a generator is anything that turns mechanical energy into electrical energy. Here is a graph. This one shows burning fuel turning a turbine that creates electricity. A generator is a direct current motor that, instead of using a battery, it uses mechanical energy to convert it into electrical energy.
Well, that's all we have on current events. Thanks for tuning in, kids, and remember, women do science too. Jill Brady, the Science Lady.